All right, so today is another topic that we're going to be looking at. We're going to move on to binomial geometric and standard normal calculations. Again, it's just a quick sort of flyover for us. There may be more to it. There may be a need on your part for more practice. But I think if I hit the highlights, at least it'll give us a place to start. And if you feel like this is a topic that's really great for you, then you only need to give it a little bit of your attention. If not, then you need to give it more. So starting out, let's recall that we had 4 rules that determine if a random variable fits a binomial setting. This is the one, and I put it in red because I can identify binomial, and for that matter, geometric right away, if each observation falls into one of 2 categories, success or failure. Either it happened or it didn't. Either we won the contest or we didn't. Either we made our weekly income goals or we didn't. So anything like that pretty much nails down whether or not you're in a binomial or, for that matter, a geometric setting. There's a fixed number of trials, right? So out of 8 kids, what is the chance of getting, 4 boys? That's either your kid is a boy or the kid is not a boy. And there's fixed number of trials, 8, so it's pretty much binomial. Your n observations must all be independent. Births are independent. And the probability of success is the same for every observation. So if you got those 4 things going, you're in binomial. All right, sorry about the little dot here. Couldn't get rid of it. The mean for a binomial distribution is just n times p. And remember, this is your shorthand notation for it that you really like to give to the AP people if you're answering a question that suddenly becomes binomial. That's a quick way to identify it, and they really like for you to identify it. Standard deviation, n times p times 1 minus p, is actually variance. So if you take the square root of that, then it's standard deviation. All right, so here's the formula for it. I believe all of these formulas are on your formula chart, but n is your number of trials, k is the probability of success, and p is the probability of success. All right, so definitely this formula for means, definitely this formula for standard deviation, not so much this one. All right, so AP requires, if you're doing an FRQ question and you think, whoops, that's binomial, then go with the capital B parentheses n and p, or name it, random variable x is binomial with n equals something and p equals something. That's your shorthand. And then get your calculations right. If you identify in words or in this symbolic way that you're in a binomial setting, then you're okay to do your binomial PDF and CDF calculations. Otherwise, they don't honor the calculator speak as identifying the distribution. Okay. And again, your formula chart is your friend. All right. Well, let's go ahead and work out some of these things. Just let's see if I can get this to close. Come on now. There we go. All right. So I have written these down, and we've got 7 kids, and we're looking for the probability of girls, right? So let's see. The birth will either be a girl or won't. Probability is the same. All births are independent. And what's the 4th one? I forgot. Oh, there. Did I say independent? All right. Fixed number of trials. Okay. There's always one that I don't recall. So let's go to the calculator. And you can do this either on a page or on a scratch pad. You really don't have to link it to anything. So the first one was the probability of 5 girls. That is a PDF because it's an exact value. So it's just menu 5, 5. And we're going to have to look for binomial PDF, which is right there. So, oops. All right, and so n is 7 because it was out of 7 births, and the probability of success is 0.5, and we're looking at exactly 5 girls. So hit OK, and there's your probability. The next one was for 7 girls, and the nice thing is once you've got this up here, you can highlight it, hit enter, and just change whatever you need to change. So I'm going to delete that, put in a 7, and there you go. There's a pretty small chance, less than 1%, that all 7 of your kids are going to be one single gender. But it's not 0. It can happen. All right, at most 4 girls. That's 0 or 1 or 2 or 3 or 4. That is a CDF. So we're going to have to go back into the menu, 5, and hopefully I won't have to struggle too much to find Binomial Cdf. Should be this one right here. Keeps going, of course. See if I can get back to it and just hit enter. All right, so that again is 7 trials. Probability is still 0.5. We're doing 0 to 4. So that's the key to getting these right, is to think, what is my range of values that I need? And hit OK. All right, that's a pretty strong chance. At least 4 girls is 4 through 7. All right, so we're going to have to change the lower value here to 4. And we're going to have to change, oops, thinking ahead, so that's 4. And then we'll change the upper one to 7. All right, there's a 0.5 chance. Between 2 and 5 inclusive, all right, that's just 2 to 5. So we're going to change the lower number here to 2 and the upper number to 5. Now, if they hadn't said inclusive, it would be 3 and 4. It would leave out the ones on either end. All right? More than 4 girls would be 5, 6, and 7. So let's go back up. It starts down at 5. So change that 2 to a 5. And change that to a 7. All right? And the last one, less than 4 girls, is 0 to 3. So let's copy that. The low number is, is going to be 0. And then the high number will be 3. All right, so very quick, very easy. It's just a matter of making sure that you've got a grip on it, okay? So getting back to our PowerPoint, let's go on to the next thing, and we're going to look at geometric, all right? So geometric also has 4 rules, 2 possible outcomes, either something happens or it doesn't, yes or no. Independent trials, that's the same as binomial. The probability of success is constant for each observation, same as binomial. All right, here, what the random variable represents is where it differs. N represents the number of trials until the first success occurs, right? So n can never be 0. Remember that. You can't get a success if you don't, perform a trial. All right. For AP, define the random variable. X is the number of trials until the first A or score of better than 90 occurs on a test or something like that. Right? So it is a discrete random variable, as is binomial. I know that puts us a little bit out of order, but that's okay. All right, here are all the formulas. Probably this is just, the basic formula for geometric. I imagine that'll be on your formula chart. It used to be that geometric was not a big part of the AP exam, but this year it has a new emphasis. It's one of the new reforms that they put in for this year for AP statistics. Mu of your random variable, the expected value or the mean, is 1 over p, and then your standard deviation is the square root of 1 minus p divided by p squared. Hopefully all of these will be on your formula chart. All right, so working out geometric problems. What's the probability that the first son is the fourth child born. Now keep in mind this is open-ended, so there's no way it can be a fixed number of trials. It's not out of like 3 births or 8 births or whatever, all right? So the probability that the fourth child is going to be your first son, it's just going to be a geometric PDF. Remember, menu 5, same menu as binomial, and then 0.5 and 4. All right, it's a PDF, so you only need one value here. So what's the probability the first son born is at most the fourth child? Well, that'll be the first, second, third, or fourth. So this will be a CDF, and it's probably geomet CDF, but you get the idea. But it is less than or equal to 4, so it's still 0.5, and then anywhere from 1 to 4, and it's just a bunch of PDFs being added up. And what's the probability that the first son born is at least the third child? All right. This you can do 1 minus up to 2, or you can just go ahead and do low to high. That would be 3 to some really big number. Infinity, if you remember to put in, you know, their shortcut for infinity, or just put in like 1,000, and that will give you the correct answer of 0.25. All right. So standard normal calculations, let's go ahead and get out of here. I can get this thing to escape. All right. And I don't know that we'll need this, but we'll just keep it open. Why not? All right. So let's see here. I'm going to go ahead and pause for a second. All right. We're going to be looking at standard normal calculations, and this worksheet should be up and posted for you. If you want to either do it ahead of time, just pause the video and, you know, work this ahead of time and see if it matches up to what I'm doing, or you can work along with me, whatever. So suppose that a particular medical procedure has a cost that is approximately normally distributed. All right, so we can just go ahead and define this, which again, your AP people like. X is approximately normal with a mean of, let's go ahead and put the dollar symbols on here, 19,800 and a standard deviation of 2,900. All right, now that is good. You've already told your reader what you're doing, and so it kind of saves you to do normal CDF without just relying entirely on calculator speak, which the AP people don't like. Also, drawing these curves, which I have done for you, or done for me just to make them look good, that is actually really good too. Now, I wouldn't avoid drawing the curves, and it's especially going to be important for that particular problem. But anyway, so let's calculate the probability that the procedure costs between 18,000 and 22,000. All right, so this is the probability that X is between 18,000 and 22,000. All right, that's going to be the probability that Z is between, now we're going to standardize, remember, Z equals X minus mu divided by sigma. So this will be 18,000 minus 19,800 divided by 2,900. All right, so Z will be greater than that, but it'll be less than 22,000 minus 19,800 divided by 2,900. All right, now you can go ahead and convert those to, you know, the equivalent z-scores, but this is really all that the AP people want to see. So since I've defined this, I drew the curve, and I've shown, you know, how to standardize, then I can just go straight to normal CDF. So normal CDF, and remember that's also under menu 5 in your calculator. All right, my low end comes first, 18,000. And that'll go up to the high end, 22,000. You really don't need the commas. And then the mean is 19,800. Start leaving those out. And then the standard deviation is 2,900. And that will give you your probability, 0.508558. That's what my calculator gave me. At least 3 decimal places. Our standard was 4. Okay, so that is a central standard normal calculation because it's going from low to high. There's no infinities in here. All right, the next one, that the procedure costs less than 15,000. So it's going from negative infinity up to $15,000. So this is the probability that x is less than 15,000, which is the same as the probability that z is less than, all right, here we go, 15,000 minus 19,800 divided by 2,900. All right, I've already, like I said, drawn my curve, defined the random variable, so this should just be normal CDF. Now when you do this, the low end comes up with some kind of like negative 9E999 or something like that. You can leave it like that or just put in a really small number. And so I put in negative 100,000 up to 15,000 with 19,800 as my mean and 2,900 as my standard deviation. And that gave me an answer of 0.048945. So if you were to just pick a procedure out at random from all these different hospitals, you would see something this low or lower about 5% of the time. Okay, so let me scoot this up a little bit. There is a little trick to it. So let me get this going. All right, and let me get that over here and get rid of it. Okay, procedure costs more than 1,700. We did the left tail. Hang on. We did the left tail. We did the center, and now we're going to do a right tail. And more than 17,250, that actually starts your interval below the mean, right? So keep in mind that this is going to be 50% of your curve. This is even more. So we're going to, and since it's a central value, it's going to add a lot of probability on here, maybe 0.7, maybe 0.8, it would be my guess. It's always kind of good to get an idea of what you might expect for an answer. So this is the probability that x is greater than 17,250. All right, that's going to be the same as the probability that z is greater than 17,250 minus 19,800 divided by 2,900. So again, normal CDF. All right, so we're going from 17,250 up to infinity, right? So I'm just going to put like 100,000, some big number, 19,800 and 2,900. And you're going to end up with a pretty big value, 0.810384. All right. That makes sense. I said it could be about 0.7 or 0.8, and that's what it ended up being. Let me get that rounded. Okay. So we did a central calculation, left tail, right tail. Now we're going to do kind of a back standardizing. It says, what is that cost? All right, it's a particular cost, so that's an x value. So when we have z equals x minus mu over sigma, let me get that right. That looks like a terrible sigma. All right, we're actually looking for that value. So we need z, we know mu and sigma. so we've got to do an inverse norm to get z. It would put the procedure in the top 10% of all procedures of this kind. All right, this is your top 10% right here. All right, since inverse norm goes from left to right, like so, you really need what's on the other side of this cut point. So it's going to be inverse norm 0.9, and that is your z-score. All right, so x minus 19,800 divided by 2,900, and that will make you greater than or equal to 1.28155. Multiply each side by 2,900, add 19,800, and you're going to get x should be greater than or equal to, okay, you need your units, 23,516.50. So anywhere this much or higher would represent you being in the top 10%. Now, it didn't use the word minimum. If it had used the word minimum, then this would be my answer, and I would have just equal to instead of an inequality. Okay? All right, so that's kind of the standard stuff. I'm going to show you how this can be modified somewhat. So if you choose 200 patients at random, approximately how many would you expect to find that paid more than 17,250? Okay, now we know what the probability is for any one person paying that much, right? That is going to be this, right? And just think, they either pay that much or more, or they don't. Sounds binomial to me, all right? So let's just say here that x is binomial. All right, it's n and p, so it's 200. And p is going to be 0.810384. All right, so now we can just go ahead and figure out how many we would expect. Now, expect is another way to say mu, and mu equals n times p, right? So here mu of x equals 200 times 0.810384, and our answer for this would be 162.077 patients. And since this is an average, we are allowed to keep the decimals. I know that there's not really a 0.077 patient or of that patient running around, but we can just, report this as being slightly more than 162, right? If you wanted to round it, I'm thinking the AP people would be fine with it. Okay, so we're down to just one more thing. So I got to get this back up here, and we need to scoot this up. All right, so let me dispense with that. All right, now this is going to be different. For a sample of 12 patients, all right, n equals 12 is a sample of 12 patients. What is the probability that they paid an average of more than 17,250? All right, this is an X bar for 12 patients. All right, so this problem is not just straight standard normal curve. This is a sampling distribution question. And we can do normal calculations on it, because if you go back to the beginning of the problem, it says that the population is normal. That means all of the sampling distributions are normal. So you're not relying on the central limit theorem or graphing or anything. Normal population, all your sampling distributions, whether they're size 2 or 20 or 80 or 1,000, they will all be approximately normal. So we can say here that X bar, the sampling distribution for X bar is approximately normal. It should have the same mean as the population distribution, The standard deviation, remember, has to be adjusted. So that'll be 2900 divided by the square root of 12. All right, see the difference? So to continue, this is the probability that x bar is greater than or equal to, it doesn't really matter, it's continuous, you could do either way, 17,250. That's the same as the probability that z is greater than or equal to 17250 minus 19,800. Sorry, I keep jumping back and forth between putting that comma there. Over 2,900 adjusted by the square root of 12. All right? And now that we've done all of that, we've defined the random variable, we've shown the standardizing, we can just go ahead and do normal CDF. And this will be 17,250 up to whatever, 100,000, something big. And your mean will be 19,800. And you can actually put this in your calculator as 2,900 over the square root of 12. In fact, I may just do it. So you're going to get 0.9984. Now remember, the one that we did earlier with it just for a single person was 0.81384. So we're going to see this thing amplify when we do groups of 12. All right, so going back to your calculator, let's go ahead and do this. So this will be menu 5, 5. And here's your inverse normal, and here is your normal CDF right here. All right, so the lower bound here is actually 17,250, so we need to delete that. And the upper bound was limitless, so you can just put 100,000, some real big number. All right, the mean here was 19,800. And here's the standard deviation. You can just put it in as a division, 2,900 divided by, and I'm just going to put this in parentheses. I don't know why. You probably don't need to. Control square root 12. Close that off. And just tab to OK. And it should be fine. All right. So that's today's lesson. I hope that it was helpful to you. I'm going to go ahead and sign off, and I will see you next time.